Hi and welcome to today's video. This is a Leaving Cert Higher Level Trigonometry Review. So we're going to look at what you need to know before you start looking at exam questions. We also have a video that goes through some exam questions examples, and that's linked in the description below. So what we first think about is what we would have seen at trigonometry at junior cert, and that would be everything got to do with right angle triangles. So we have Pythagoras theorem, we have sine, we have cosine, cos, and we have tan, tangent. We also then add in for leaving cert the formula for non-right angle triangles. So we have the sine rule and the cosine rule. We look at then the measure of angles. So they can be measured in degrees. Degrees can then be broken down further into degrees, minutes, seconds, and then there's also radians. We'll look at the unit circle and we'll look at trigonometric functions. So specifically understanding the difference between the period, the range, how to get that from the graph, how to take that if you're given the actual function to draw the graph. At this point, what I'll say is trigonometry is a topic that we see across both papers. It is primarily a paper 2 topic. However, given the section we have here on functions, it is actually common to see that appear on paper 1. Bear that in mind. We also have trigonometric identities, and you need to know trigonometric proofs. So these are short little proofs that you need to know off by heart. So here we have a right angle triangle. And before we look at the actual formula, it's important that you understand some of the language around it. Here we have the right angle given by that little square on the left hand side. That's how we know that it measures 90 degrees. It could also be written as an L. The hypotenuse is always the longest side of the triangle, and it is across from the right angle. That means that only right angle triangles have a hypotenuse. Other two sides are known as the leg of the triangle. So now let's talk about Pythagoras' theorem and also the converse of Pythagoras' theorem. So Pythagoras' theorem is one that sits between both trigonometry and geometry. So because it sits in both, we can look at it from more of a trigonometric point of view. So working with Pythagoras before working with our sine, cos and tan, or our trigonometric ratios. Or we can look at it from a more geometry point of view. So we might be using Pythagoras' theorem and then work with our other theorems we have from geometry, such as all the angles add up to 180, etc. So here we have the theorem of Pythagoras, which basically tells us that the square of the hypotenuse is equal to the sum of the squares of the other two sides. This is specifically when we have a right angle triangle. The converse of this theorem says if the square of one side of a triangle is the sum of the square of the other twos, then the angle opposite the first side is a right angle. So basically, if we don't know that the triangle is a right angle triangle, we can use the Pythagoras theorem to prove that it is a right angle triangle. And we know then whatever side is the longest must then be the hypotenuse. So this leads us to something called Pythagorean triples. So this is a term that does tend to come up, and we've seen it at both junior cert and leaving cert. And basically the term Pythagorean triple means three numbers such that put into the formula they satisfy c squared equals a squared plus b squared. So the example here is 3, 4 and 5. They form a Pythagorean triple because 5 squared is equal to 3 squared plus 4 squared. And remember, the hypotenuse when we're talking about a right angle is always the longest side. So this will always be the square of the longest side, or in this case the biggest number, will equal to the sum of the squares of the other two numbers. So there are infinitely many Pythagorean triples, but here are some examples. Often as students work with trigonometry, they start to notice these Pythagorean triples, and they start to notice that when you have 3 and 4 and you're missing the hypotenuse, hypotenuse will always be 5. So they start to see these patterns emerge. So we have 3, 4, 5, 5, 12, 13, 7, 24, 25, and so on. So now let's look at labeling a right angle triangle. So we've labeled it for Pythagoras. So when we were dealing with Pythagoras, we still talked about this being the hypotenuse. Well, what if I instead said, well, let's talk about the labeling of a triangle with respect to an angle. And our angle here is A. So suddenly which side is which becomes a lot more important. So when we dealt with Pythagoras, we said the hypotenuse, yes, that was really important. We identified that correctly. But the other two, it didn't really matter. Now the other two sides, it really does matter because we're talking about this angle here. So our other two sides are labeled as opposite, meaning opposite the angle, and the second is the adjacent. And adjacent is another word for beside. It's not a term we use a lot in English anymore, but it is an English term for beside. So it is the side beside the angle. So my advice, and the way that most students prefer to work, is first of all label your hypotenuse, then label the side which is opposite, and then adjacent is the final side left, or it's the one beside it. That tends to be the one that students find most difficult to remember. So we have three trigonometric ratios that we needed at junior cert higher level, and they are the sine ratio. So sometimes mispronounced sin because it's S-I-N, but that's just short for sine, S-I-N-E. So the sine ratio here, and the sine of A is given as the opposite over hypotenuse. So there are two sides there. So in this triangle, our opposite side, bear in mind, is always opposite our angle. So then we have the cosine ratio, or what's known as cos. So cos of A is equal to the adjacent over the hypotenuse. So in this case, we're talking about the angle is beside the side. So that side that's beside the angle. So adjacent. And the last one is our tangent ratio, or simply known as tan. Tan of A is equal to opposite over adjacent. Okay, so again, remember, I'm constantly looking, the angle is opposite. Okay, so notice that in each of those ratios, because we have three sides, there is one side missing. So the sine ratio does not use adjacent. The cosine does not use opposite, and tan does not use hypotenuse. And that's important to remember because one of the big questions students have is, how do I know which one I should use? And in most cases, only one will be able to be used because of the information we have. If you have all three sides, then you can use any one you want and it won't make a difference. So one way that students remember this is using SOHCAHTOA. Now, one of the drawbacks of using SOHCAHTOA is, do you know how to spell it? So if you use SOHCAHTOA, first of all, make sure you know how to spell it. So SOHCAHTOA. And that is a way for us to remember that sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. Sometimes people make up little rhymes to go with the letters. So one is silly old Harry caught a herring trawling off America. There's lots of different versions that I've heard. Remember that these are also available in your log tables. Now, when we're working with our log tables, they can be a little bit tricky because they don't call the sides opposite, adjacent, and hypotenuse, which often exam questions want you to label your sides as that. So although we do have these formula and you could work with your log tables, it is not the best idea to do so. So a really important idea you need to understand is that tan is the same as slope. So we use them in different contexts, but effectively they measure the same thing. Slope is a measure of how slanted a line is. Tan is a measure of how slanted a hypotenuse in a right angle triangle is. Let's take a look at a line here. We have our x and y axis and a line. If I wanted to get the slope, I'd use the idea of rise over run. Okay, so my slope is rise over run. If I then put a right angle triangle on top of that, effectively what we had already made, given our angle A here, this side is opposite and this one is adjacent. So rise over run would be the same as opposite over adjacent, which is the same as the tan of angle A. So be really clear about that connection between tan and slope. The formulas for right angle triangles are available in our log tables on page 16. I'm not a big fan of the sine, cos, and tan formula that are here. I prefer using SOHCAHTOA or Ciliotari or something like that to remember them in terms of opposite and adjacent. Most of you will have learned that at junior cert, but just if there was an issue, the formula are here, and the Pythagoras theorem, c squared is equal to a squared plus b squared, is also here. Then we look at the formula for non-right angle triangles. Again, this is on page 16. Notice that this page 16 is split into the two parts. Right angle triangles at the bottom, and the top one where it says trigonometry of the triangle, these are non-right angle triangles. These formula, and I'll show you these here, can be used if the triangle is a right angle triangle, but you're doing too much. They're an extra piece of work that's not required. If it's a right angle triangle, our lives are made easier and we can use the much easier ratios below. We have an area formula here, and this formula also appears on the area page of our log tables. We have a sine rule. Bear in mind that if you're working with the sine rule, you can use them as is, or you can use the reciprocals. So if I ever need to find the angle, I would tend to use the reciprocals. So what that means is you flip the fraction. So sine of A over A is equal to sine of B over B is equal to sine of C over C, and so on. At cosine rule, A squared is equal to B squared plus C squared minus 2BC cos A. We tend to use sine rule when we have two sides and two angles. So that might be you have one angle and you need to find the other. In cosine rule, we're talking about the three sides and one angle. So when we talk about the sine rule, it's important to note that there is an ambiguous case. If you have not already looked at the unit circle or revised the unit circle, I would advise you to do that now. What I'm going to talk about now relates to the idea of the unit circle. So let's look at the triangle ABC. So given the angle CAB, AC and BC, there are actually two different triangles you can draw. So what I mean visually by that is here. If I told you the angle at A, highlighted in yellow, AC, that length there, and BC, there's actually two lengths. So think back to your constructions. That would be talking about having side-side angle or angle side-side. Neither of those allows us to say that triangles are congruent. Congruent is another word for identical. Remember, for congruency, we have side, 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 side angle side, angle side angle, or right angle hypotenuse side. So if you knew two sides and an angle, that angle has to be in between. So side, angle, side. The angle has to sit between the two sides. If it doesn't, we have this issue here. We have what we call an ambiguous case. There are two possible triangles with the same measurements. So if we work with the sine rule, it is possible to get two answers for an angle or a size. So when we talk about this, it's linked to the unit circle. So because when we talk about the unit circle, cos is positive, all is positive, sine is positive, tan is positive. We are talking about a triangle. A triangle has in total 180 degrees. That means angles are either going to fit in the first quadrant, and they are the acute angles, and most triangles are that. And then we have the obtuse angles over here. Now, obtuse triangles will have a positive sign. So an obtuse angle will also have a positive sign. So we're stuck. We're stuck with this idea of when we're dealing with sine, and we have sine of an angle equals a given number, and we work backwards, we could actually be dealing with a triangle with the ambiguous case. So there would actually be two possible triangles we're talking about. Let's see how this would come up in a question. So now let's talk about the measures of angles. Everyone at this point should be very familiar with degrees, but what happens is we are a little bit less familiar with the breakdown of degrees. So angles are in general measured in degrees. Degree symbol is our little circle. As you move into Leaving Cert higher level, you will learn a new way to measure angles, but for the moment we're focusing on degrees. Now, each degree is actually split into 60 smaller pieces, and each of those smaller pieces, which are 1/60th of a degree, are called minutes, and its symbol is just like a little dash. Then each minute is split up into 60 again, and each of those, which are 1/60th of a minute, are called seconds, and they have a little double dash there. So for example, an angle could be 40 degrees, 20 minutes and 50 seconds, which is written as 40 degrees, 20 minutes and 50 seconds. So most of the time we're dealing specifically in degrees, but we do often see questions that ask us to turn the degrees in decimal form back to degrees, minutes, seconds. And I suppose the minutes and seconds mirrors time, and I suppose it's to remember, if you think how many seconds are in a minute time wise, it's 60. How many minutes are in an hour? 60. But here we have how many seconds are in a minute, still 60, and how many minutes are in a degree, and that is also 60. So they definitely mirror each other, and it's one to remember. We have a button on our calculator that's going to make our lives so much easier with this, and it's here. It's the degree, minute, seconds button. If you're using a sharp, it actually says DMS, degrees, minutes, seconds. Here it is actually the symbol for degrees, for minutes, and for seconds. A little bit hard to see in my picture here, but there's a close-up of the button on the next slide, so hopefully we'll get a better chance to see it. But best thing for you to do is to take your calculator and see, can you find it. So what we're going to talk about now is a new type of measurement, and that measurement is called radian. So before we do this, I would just suggest that make sure you know how to change your calculator between degrees and radians. You should, depending on your calculator, have something which lets you know either it says or at the top or RAD if you're in radian measure, or it might say D or DEG if you're in degree measure. Make sure you're in one of those two. There is a third measure on the calculators, but we're only ever going to deal with degrees or radians. So a radian is the measure of an angle at the center of a circle subtended by an arc equal to its length in radius. So first of all, let me explain this subtended. So basically it's just a fancy word which means that an angle at a particular point where straight lines from its extremities are joined at that point. So basically a radian is the measure of an angle at the center of the circle subtended by an arc. So basically the lines are coming in from either end of that arc. And if you look at that picture there, we have radius or and the arc length or, and that's what creates our 1 radian. So building on that, the circumference of our circle is 2 pi r. So that's something you've probably been using since primary school. The formula for a circumference of a circle, 2 pi r. So basically that's saying it's 2 pi times the radius. So basically, breaking down our definition, which says, well, if the arc was r, then that's 1 radian. So if we're saying 2 pi r, there must be 2 pi radians in one complete revolution. So that means 360 degrees, 1 revolution, 2 pi, 1 revolution. That creates this idea, or this link between radians and degrees, which means 2 pi radians equals 360 degrees. Having that, pi radians must be 180 degrees, and having that again, pi over 2 radians must equal 90 degrees. Going, I suppose, to our 4 points we had on our previous slide, we can say that 3 pi over 2 radians is 270. So how you would probably work to that is, well, 90 degrees to get to 270, multiply it by 3. Pi over 2 radians, multiply it by 3, and that gives you 3 pi over 2 radians. So I'm going to draw your attention to your formula and tables book on page 13. So there are actually 4 pages for trigonometry. It starts on page 13. We go 13, 14, 15, and 16. You probably have really only seen page 16. That's the one that has Pythagoras on it, and it has sine, cos, and tan. If anything, sometimes students don't even use that page at junior cert. So what I'd like to point out on this page is a really, really handy little table that appears at the bottom. And what it gives us are some of the main values for sine, cos, and tan for some of the main angles. So we have 0 degrees, 90 degrees, 180 degrees, 270 degrees, 30 degrees, 45 degrees, and 60 degrees. What's really nice about this table is it also gives us radians. So this line here actually gives us radians. So here we have our, we have our pi is 180, we have 3 pi over 2 is 270, they also give us 30 degrees, 45 degrees, and 60 degrees in radians. What I like about this particular table on page 13 and why I'd suggest to students to have it open is, well, one, it's a lot quicker than going to your calculator for answers. It also gives us a really, really nice way to move between degrees and radians very, very quickly without having to worry about, is our calculator in the right mode? Because that can make a huge, huge difference, and you'll know as you start to work, if that happens to you, you'll see very quickly the numbers, the difference in the numbers, it's huge. So having this page open in front of you means you're not going to be as worried about changing between degrees and radians. So it makes life a little bit easier. It also gives us a really, kind of an estimate for converting radians to degrees and for degrees to radians. But what we're going to do is we're going to think about the fact that 2 pi equals 360 degrees and 180 degrees equals pi. So we're going to focus on this part here, and we're going to use that for a really, really accurate conversion. So now let's talk about the unit circle. So the unit circle is a circle with center 0, 0 and radius 1. So this is our unit circle there, so called because the radius is 1 unit. So you can see some points on it that are quite obvious. So if it has a center 0, 0 and radius 1, we have our point 1, 0 here, our point 0, 1 here, our point minus 1, 0 here, and our point 0, minus 1 here. So this simple circle is an easy way to work with angles and ratios. When I talk in ratios, I mean my trigonometric ratios. So here is another example of a circle where, well, this is still the unit circle. We can see our radius here is given as length 1. So it says let P, X, Y be any point on the circle as shown. And we have a triangle here where we just have OPC. And it's a right angle triangle. So we drop a line vertically down from P to create that right angle. So we have this triangle here. If that point P is XY, that gives us our X along the X-axis and Y, this vertical height here. It's a unit circle, so we have 1 as our hypotenuse in this triangle. So working with our sine, cos, tan, so our theta is here, this becomes opposite, this becomes adjacent, this is hypotenuse. How do you remember sine, cos, tan? So if you're using SOHCAHTOA, or if you're using any little phrase to help you, write that up so we can see it. So if we work out cos, adjacent over hypotenuse, that's adjacent is x, hypotenuse is 1. So x over 1 is cos. Okay, so that's my adjacent over hypotenuse. X over 1 is just x, so it actually gives me cos of theta is just x. Similarly, we can work with sine, which is opposite over hypotenuse, and sine of theta is y over 1, so sine of theta is just y. So therefore the coordinates of P, instead of being x, y, we could actually say in this unit circle that they're actually cos theta, sine theta. So what we have here is sine theta is the y coordinate of P, cos theta is the x coordinate of P, and then we end up with tan as the gradient, or another word for gradient is slope, okay, of OP. So just take a look what that looks like for a second. So there's P and here's our angle. So as we move that angle, as we move P around, what we're seeing is we're getting a bigger angle, but each of those points can actually be written as cos theta, sine theta. So the point P can in each case be written as cos theta, sine theta, where theta is the angle between the positive sense of the x-axis and the line OP. So bringing it back to your formula and tables book, again on page 13, I'm actually going to focus on this little diagram here. And what we have here is actually our unit circle. So we have a unit circle given with the angle A. It gives us the point on the circle, which is cos A sine A. It gives us the 4 points on the circle that we'd already pointed out at the very start. So 1, 0, 0, 1, minus 1, 0, and 0, minus 1. And basically what this tells us is when we have the unit circle, this x-axis is actually the cos axis and the y-axis is actually our sine axis. So we can do a lot with this unit circle and it can help us to answer a lot of different questions. So the last thing I want to point out on this page before we move forward is this formula here, which is the tan of angle A is equal to sine A over cos A. I want to work with this a little bit more just to explain where we got this idea of the slope. Because cos and sine, really obvious, well hopefully really obvious from this unit circle. I want to talk a little bit more about tan. So what I have up here in the top right hand corner is just a little bit on our quadrants again. So we talked about that at the start of the video, but first quadrant, top right hand corner, and then it goes second quadrant, third quadrant, fourth quadrant. So here's my unit circle, and what I want to talk about is this idea of a reference angle. So every angle in the unit circle has a related reference angle, and the reference angle is always acute. So the reason we work with acute angles is because that's what we've always worked with. It's much easier to work with, and if we can bring everything back to a simpler acute angle, it makes all of our questions very easy. When I talk about the first quadrant, I'm talking about this angle here. That angle is already acute. Okay, so angle is already acute. And that means the angle that we have equals the reference angle. So not a big deal. Everything is the same. Second quadrant. So we're actually moving like this. Now, my reference angle is actually this angle A. Our actual angle is this angle theta. So our reference angle A, that is equal to 180 degrees minus my actual angle theta. So the reference angle is this acute little angle which we find in against the positive x-axis. So in the third quadrant we have this angle theta here. It is a reflex angle. So our corresponding reference angle is this one here. So how we would work that out, A is going to be our theta take away 180 degrees. And finally, in our fourth quadrant, we have theta, that is this angle here. Our reference angle is this little angle here. That means my reference angle is equal to 360 degrees take away theta. So we can always work out this acute angle, this reference angle, no matter what size angle we're given. So this is it in summary. So what we have here is our theta here is our little acute reference angle. And something else interesting pops up from here, and it's this idea of, well, where are sine and cos and tan positive and negative? So remember my y-axis and my x-axis. X-axis is actually the cos axis and y is actually the sine. So here in the first quadrant, our x and y are both positive, so cos and sine are both positive. Remember our little formula, which was tan is equal to sine divided by cos. That means to calculate tan, it's a plus divided by a plus, so tan is also positive. So that's quadrant 1. In quadrant 2 then, over here, we have, well, the x-axis becomes negative, so cos is actually negative. The sine is still positive. To get tan, we divide a positive by a negative, so it will be negative. So that's our second quadrant. Third quadrant down here, we have, well, cos is still negative. Our sine is now also negative. Negative divided by a negative to get tan, so tan will actually be positive down in this quadrant. And our final quadrant, quadrant 4, we have cos is positive, sine is negative, tan is positive divided by a negative, so tan is now also negative. Okay, so we're able to see, depending on which quadrant it's in, whether sine, cos, or tan is positive, negative. So in short, we're able to do this C-A-S-T. What that stands for, C stands for cos is positive, A stands for all are positive, S stands for sine is positive, and T stands for tan is positive. So there's lots of different ways where you can remember this. Cast, I think, is the easiest, C-A-S-T, starting from the bottom and working around, but whatever way you can remember it. This can all be worked out very easily, especially using page 13 if you get stuck in your exam. So just some terminology around our function. So we have the period, so that is the length of time it takes to make one full rotation, and it can easily be measured as peak to peak, but you can measure it in whatever way you like as long as you take a full rotation. So for the basic trigonometric graphs, the period is 2 pi. Now I say basic like the ones we've just seen, and that's before any transformations get applied. So the frequency is 1 over the period, and for basic trigonometric functions, it's given as 1 over 2 pi. We're going to see how that changes slightly as we move into the transformations. And the range of the function, first of all, the amplitude is like its height from center, okay? So the center line to the peak, the amplitude. So therefore, the actual range, so from min to max, that's like twice the amplitude. So when we ask for the range of the function, we give our minimum point and our maximum point. For basic sine and cos graphs, it's -1 to 1. For our tan graphs, because they can take any value, it'll be -infinity to infinity. So here are our graphs, and we have sine, cos, and tan. We have our periods are all 2 pi. We have our range for sine and cos are -1, 1, and for tan is -infinity to +infinity. And we have our asymptotes here as well on tan at 90 and 270. That means that there are no values for tan at 90, tan at 270. And if you want to throw that in your calculator, and what you're going to get out of it is an error. Think of tan like your slope. So basically we're asking what's the slope of a vertical line, and we always say that that is undefined. We were never able to get tan of 90 degrees when we were doing junior cert, because we were dealing with 90-degree, well, we're talking right angle triangles. So if I have a right angle triangle, the other angle couldn't be 90 degrees because then it wouldn't be a triangle anymore. There would be no third angle. So just talking a little bit about transformations of these graphs. So the transformation, we really only have to worry about sine and cos, not so much tan. Tan, there's other questions that can be asked for tan, but really the focus is going to be on sine and cos. And we're going to do some exam questions, and you're going to see that that is where the focus is. The general graphs basically have a sine nx. So for example, there is a coefficient in front of sine. So what that does is it stretches out, just like putting a constant in front of any function that we've seen before. It stretches it. So what that changes is its range. It goes -a to a. It should be -1 to 1. So therefore, if you multiply 1 by that a, it's going to give you -a and a. the period also changes. So putting n in front of x, what it does, it actually kind of squeezes the graph together. So it actually creates this compression. And that's going to give us a new period of 2 pi over n. So that's how quickly it's going to move through its full rotation. So it's going to move through a little bit quicker. So just be aware of that. So the two pieces, and the good news is it works the same for sine as it does tan. So there's my n and there's my a's. So here a cos nx, there's my n, there's my a's. So when you have an idea how it works for one, you'll have a great idea how it works for all. It'll make a lot more sense as you see it work through here in exam questions. So we need to understand a bit more about trigonometric identities. Identities tend to be something that is given as like a show, and we start with one trigonometric identity and we need to get it to look like another. Just to make a distinction here between an equation and identity, an identity is an equation that is true for all values of the variable for which the expressions are defined. So we would have met with identities in algebra. You might call them unknown coefficients. And it's just a little bit more than the equation, and how we kind of make that distinction is an equation we tend to want to solve for x or whatever that variable is. In terms of an identity, we don't really care about that variable. It's more about using the idea that the left-hand side equals the right-hand side and figuring out something about the identity. When we're working with trigonometric identities, there's a lot of different places where we can go. This can be quite overwhelming for students, and the best advice I can give is to just practice lots of these questions. At the top of page 13, we have tan, sec, cot, and cosec. On the left hand side, we then have what is possibly the most important little identity, and that is that cos squared a plus sine squared a equals 1. That comes from our unit circle. We then have sec squared a is equal to 1 plus tan squared a, and then we have a little bit below about negative angles. The identities also appear on page 14 and page 15 of your log tables.